Okay, so our next topic is going to be entropy. Okay, so in our previous chapter, if you remember, we have studied some of the Clausius inequality statements. Okay, that means for Clausius inequality statement, he has said that the cyclic integration of dq by t is always going to be less than or equal to 0. Okay, that was the thing which we have seen in last chapter. Okay, now this is the mathematical form of second law of thermodynamics. Okay, this is the mathematical form of second law of thermodynamics. Now from this we have also said that dq by, if the cyclic integration of dq by t is going to be 0, then the cycle must be reversible, or we can say that for a reversible cycle dq by t, cyclic integration of dq by t is always 0. Similarly for irreversible process, dq by t is always going to be, integration of dq by t is always going to be less than 0. Now since he has not mentioned anything about greater than 0, we are considering that this is impossible, okay, or not possible. Okay, cyclic integration of dq by t greater than 0 is not possible. That means the system either can be reversible or irreversible. Okay, now he has given the conditions for reversible and irreversible. The third option is not there, so this is not going to be possible. Now in entropy we are going to consider reversible and irreversible case, and we are going to understand the concept of entropy. Okay, we are going to understand the concept of entropy by studying reversible irreversible processes separately. Okay, so now let us discuss the reversible cycle. Okay, now as we have said, we will consider reversible cycle and irreversible cycle separately, and we will try to understand the concept of entropy. So first thing we are going to take is reversible cycle. Now for example, let us, there is a plot. Okay, it may be PV, TS, anything it can be. This is a plot, and 1 and 2 are two states. Okay, 1 and 2 are two states in that plot. Okay, now what happens, let us consider 1 to 2. It is the system is changing its state from state 1 to state 2 via path A. Okay, and again let us consider 2 to 1. There is another change in state via process B or via path B. Okay, and another process is going to be there which is going from state 2 to state 1, which is via path C. Okay, that means what? In this plot, 1A to B1 forms a cycle. Again 1A to C1 also forms a cycle, forming a cycle. Okay, that means in this diagram we are considering two cycles, and all of them are reversible. This is our consideration. Okay, this is our consideration. So that means what? For, let us take the first cycle, that is 1A to B1. Okay, let us take the first cycle 1A to B1. Okay, that means it is coming from state 1 to state 2 via path A, and 2 to 1 from 2 to 1 via path B. Now if we write down the Clausius equation or inequation statement, and all of these are reversible. For reversible cycle, we have said that for reversible cycle, what was that? dq by t was 0 for reversible cycle. That means what, the cyclic integration of dq by t was going to be 0. Now if you write this thing for state 1 to 2, or for cycle 1A to B1. If you write this thing for cycle 1A to B1, this is going to be dq by t, okay, for process 1A2. Okay, for process 1A2, dq by dt plus dq by t for process 2B1. Okay, is going to be 0. Cyclic integration means what? It is going to be the integration or the summation. Okay, so we have separately written down the dq by t term for this path A, and we have written down the dq by t for path B, and these two are going to be 0. Similarly, for cycle 1A to C1, what is it going to be? 1A to C1. Okay, now that means what, 1 to 2 it is coming via path A, and 2 to 1 it is going via path C. Okay, now this, if we write this equation for this cycle 1A to C1, this is going to be dq by t for path 1A2 plus dq by t to C1. this is going to be 0, because all these processes we have considered is reversible. Okay, since all these processes are reversible, that means this cycle is also reversible and this cycle is also reversible. Now let us say that this is equation 1 and this is going to be equation 2. Okay, now if you subtract equation 2 from equation 1, what it is going to be? This thing and this thing is going to get cancelled. We are subtracting equation 2 from equation 1. Okay, now what will be remaining? The remaining thing will be this minus this equal to 0. This and this will be cancelled out. Okay, this minus this is going to be 0. That means what? dq by t for 2b1 minus this one, dq by t for 2c1 is going to be 0. Now this minus this is going to be 0. That means what? This minus this is going to be 0. That means both of them are equal. Okay, both of them are equal. That's why their difference is going to be 0. So 2b1 is going to be equal to dq by t 2c1. Okay, that means what? The dq by t term for 2b1 and dq by t term for 2c1 is going to be same. This is our proof. Okay, now from this what we are going to get? Okay, what we are going to get? Now if you see here, you can say that the dq by t, okay, dq by t term is not going to be dependent upon the path. Okay, it only depends upon the endpoints of the system. 2 and 1 are the endpoints of the system. Okay, 2 and 1 are the endpoints of the system. That means whether it is path B or path C or path A, dq by t is going to be same for all the cases, provided that this cycle is reversible cycle. If it is reversible cycle, or what the conditions will be, we will see in the next board. But till now we are saying that if any system is going to be reversible, or any process or cycle is going to be reversible, then dq by t term does not depend upon the path. It only depends upon the processes or states. Okay, it only depends upon the starting point and ending point, that is 2 and A. End points only matters. Okay, otherwise dq by t and dq by t is going to be same. Okay, now if something is only dependent on the endpoints of a system or of a process, then what does it mean? It means that this term is definitely a property. Only properties are there. Okay, we have said earlier also, only properties are there which are only going to be dependent upon the starting point and ending point of a process. Okay, now these two things are only dependent on starting and ending point. Now if these things are only dependent on starting and ending point, that means what? This is going to be a property. Okay, so since we have said that these two are the property, these two are going to be a property of the system, since it is only depending upon the ending points, these two is going to give us the entropy. Okay, these two terms are defined as entropy. That means not these two terms, we are saying that if this has been proved, that means what? If you take that dq by t for a reversible process is going to be equal, dq by t is for a reversible process is going to be equal for all the paths in reversible processes, then this must be a property. And that property is known as our entropy. Okay, that property is known as our entropy. Now from this we can write that this is equal to going to be ds. Okay, that means change in entropy is going to be 0 if we go from if only one state is considered. Okay, if only one state is considered, that means state 1 or state 2, the change in entropy is going to be 0. Okay, for a final time I am going to say that dq by t for any reversible process is going to be always same. And if this is going to be same, this is going to be same, if it is mentioned that starting point and ending point is same, if starting point and ending point is same, then all the processes comprising of reversible processes, then this term is always going to be same for all these processes. Okay, for path A this is going to be same, for path B this is going to be same, for path C it is also going to be same. Okay, now if this is going to be same, this is going to give us the property named entropy. Okay, now we are going to consider the irreversible cycle. Okay, or irreversible cycle, that means what, we will be considering all the things as same. We in the previous case what we have done, we have considered that A process is reversible, B process is reversible, and C process was also reversible. Now we are taking that C process is irreversible. Okay, it is, that's why it is given in dotted line. Okay, C process is irreversible and both of them are going to be reversible and reversible. Okay, in previous case this was also considered as reversible. Now if you write the mathematical form of second law of thermodynamics, that means this one, in cyclic integration of dq by t is going to be 0 for reversible and less than 0 for irreversible. Now there are two cycles, 1A2 B1 and 1A2 C1. Okay, 1A2 B1 is going to be a reversible cycle and 1A2 C1 is going to be a irreversible cycle. Previously both these cases were reversible cycle. Now one cycle is reversible and another cycle is irreversible. Now first of all let us take the reversible cycle. What is the reversible cycle? Here reversible cycle is 1A2 B1. Okay, this one is reversible cycle. Now if you write this equation for the reversible cycle, it is going to be same as the previous one, dq by t for 1A2 plus dq by t for 2B1 is going to be equal to 0. Is going to be equal to 0. Now from here you can write that dq by t for 1A2 is going to be equal to minus of dq by t to V1. Okay, now we have written this reversible cycle. We have written down this equation for this cycle previously also. Now this is going to be seen. The only thing we are going to do here is different. The only different thing we are going to do here is dq by t for 1A2. We are finding this value in terms of dq by t for this path. Okay, we are finding the dq by t value of this path in terms of dq by t value of this path. Now let us write the equation for irreversible process. Okay, the irreversible process is what? Here the irreversible not process, cycle. Irreversible cycle is what? The irreversible cycle here is 1A2 C1. Okay, 1A2 C1. This is the irreversible cycle. Now it is going to be less than 0 because it is irreversible. Now if you write down the equation, what will you get? We will get dq by t for 1A2 plus dq by t for 2C1 is going to be less than equal to 0. Sorry, less than 0. Since it is irreversible, this is going to be less than 0. Now if you put the value of dq by t 1A2 from here, what will you get? We will get minus of dq by t, okay, minus of dq by t for 2B1, okay, plus dq by t of 2C1 is less than 0. Okay, now from this equation, from this part we can write that dq by t for 2B1 is going to be always greater than equal to, so greater than dq by t for 2C1. From here we can write this. Okay, now what does it mean? What does it mean from here? It means that dq by t term for a reversible process, 2B1 is a reversible path. Okay, 2B1 is a reversible path and dq by 2C1 is an irreversible path. Now from this derivation we are going to understand the concept that the dq by t term is always going to be greater than, for a reversible process is always going to be greater than the dq by t term for an irreversible process. Okay, and we have said that only the dq by t term for a reversible process is going to give us the change in entropy, not the irreversible one, only the reversible one. Okay, for making it important, we need to underline this reversible. Okay, that means what? Only for reversible process, whatever the term for dq by t is there, okay, only for reversible, that is going to be our entropy or property. Okay, if it is in the case of irreversible process, it is not going to be the entropy. Okay, it is not going to be the entropy. That means dq by t for irreversible process is not equal to ds. Okay, is not equal to ds. Now here some people get confused that what if the total cycle is irreversible? If their total cycle or total process is irreversible, is there no entropy? Obviously there is going to be entropy, but we are going to define that entropy with the help of an irreversible process. Okay, that means let us suppose we have taken a plot, okay, and that is point 1, that is point 2. Okay, now from point 1 to 2 we are going via an irreversible process, suppose. Now since we have said that dq by t for reversible process is going to give us the entropy, does that mean that if 1 to 2 is an irreversible process, it doesn't have any entropy? No, it has an entropy, and that entropy is going to be get defined when we draw a reversible process. We will see a reversible process from point 1 to 2, and whatever the dq by t term for that reversible process we are going to get, that is going to be the entropy change for the irreversible process. Okay, the reversible process from state 1 to state 2 is the medium to find out the entropy of a process, whether it is reversible or irreversible. Okay, and always the reversible process dq by dt or entropy term for reversible process is going to be greater than irreversible process. Okay, now to make this understand, let us suppose that the dq by dt term for a is going to be 5. Okay, let us say that dq by t term for process a is going to be 5. Okay, now if this is 5, then for process b also it is going to be 5, but this for process c it may be 3 or 2 or 4, whatever it may be, but it must be less than 5, because we have found out that for the irreversible process dq by t term is always less than the dq by t term for reversible process. Okay, 2b1 is a reversible process. Okay, now the thing we need to understand very carefully is this point and whatever the values are going to be there. That means that if the entropy change from process 1 to 2 via a reversible path A is there, then the value of this is going to be same as that of the path B. Okay, that means the entropy change via path B while it is coming from state 2 to 1 is always going to be same. Okay, for all the reversible cases. In the last board we have seen that if the reversible cases are there, then dq by t term is always going to be equal. Okay, these two are going to be equal, and from this point we are going to say that this thing is never going to be equal to 5. This must be less than 5. For this process, change in entropy must be less than 5. It may be 3, 2, 1, 4.5, 4.9999, whatever it may be, must be less than 5. Okay, and if a reversible process is there, this thing I am saying again, if a reversible process is there from 1 to 2, it does not mean that there is no entropy change or we cannot find entropy change. Okay, because we have said that this is going to be the entropy change. dq by t for reversible process is going to give us the entropy change. That does not mean that if a process is irreversible, we cannot find the entropy change. If from process 1 to 2 there is an irreversible process, first of all we need to find a reversible process from state 1 to state 2, and we need to calculate the dq by t term for that reversible process. We are drawing a reversible process from point 1 to 2, and from this reversible process we need to find out the term dq by t for reversible process, and that thing is going to give us the entropy change via whatever path you come to point 2, whether it may be reversible or irreversible. the entropy change is going to be given to us with the help of the reversible process. Okay, the reversible process, dq by t term for reversible process from 1 to 2 is going to give us the entropy change for any process, whether you come from here, whether you come from here, whether you come reversibly or irreversibly. Okay, this term is going to give us the entropy change, whether it may be reversible or irreversible. In some interviews they always ask such type of confusing questions. Okay, they will ask if there is a irreversible, you will always say that if someone asks you what is entropy, okay, what is entropy, so we always say that if for a reversible process, if there is a term dq by dt for any process in a reversible process, then this is going to give us entropy. Now they will ask, what if there is a reversible question, then what is going to be the entropy? Then some people get confused. You need to say that for if there is a process which is reversible, we will have to do the calculations for this process reversibly. Okay, that means we need to imagine a process which is reversible. Okay, similar to this process only, from going from process 1 state 1 to state 2 via a reversible path. And for that reversible path, whatever the dq by t term or whatever the entropy changing term we are going to get, that term is going to give us the change in state for irreversible process. Okay, when the initial state and final state is going to be same. Okay, that means the same point. If there is a irreversible process, we need to imagine a reversible process, then we need to calculate the change in entropy from that reversible process, and that reversible process change in entropy is going to be same as the change in entropy for irreversible process. Okay, now this is the concept of entropy from irreversible cycle. We have seen both the cases. Okay, in both the cases we have seen that for reversible process, dq by t term is always going to be same. Okay, and reverse process dq by t, reversible process dq by t is always greater than the irreversible path dq by t term. These are the two conclusions which we have got from case 1 and case 2, that is reversible cycle and irreversible cycle. Okay, so now we are going to see the conclusions what we have done till now. Okay, so I am going to read it once because I have said this earlier also. So between two endpoints, if number of reversible processes are there, then for each path the term dq by t reversible is going to be same and is a property. Okay, so we have said this earlier in the reversible part. Okay, when we are deriving the reversible part, we have said that between two endpoints, if there are number of reversible processes, then each of the reversible processes having this term is going to be same. Okay, and this term is going to be a property. Okay, must remember that this must be a reversible. dq by dt for reversible is going to be same and it is going to be a property. dq by dt irreversible is not a property. It is just a quantity which is less than entropy. Okay, this is the entropy and this is always greater than this one. You have derived that also. This is always greater than this one. Okay, now this is just not a property. This can be different for different irreversible processes. This is just a quantity which is less than this one, which is less than the property. Okay, now in order to find out the entropy change of an irreversible process, it must be replaced with a reversible process of same endpoint. That thing also I have said that in interview questions, whatever they are asking, that in order to find the entropy change of an irreversible process, what we are going to do, we are going to replace that process by a reversible process. Okay, then we are going to find out the entropy change for that reversible process using this one, and then whatever the term is going to be there, this is the same, this entropy change value is going to be same for that irreversible process also. Okay, so now we are going to read about entropy change in reversible processes. Okay, now we have considered some reversible processes and we are going to see what is going to be the entropy change in that system. So case 1 we are going to take when heat is added to the system. Okay, when heat is added to the system. When heat is added to the system, that means what? We have already mentioned that we are going to consider reversible processes. Okay, now for reversible processes we have seen that change in entropy was going to be dq by t. Okay, this was our formula, okay, for entropy change. Okay, now since we are going to consider reversible, that's why change in entropy is going to be this. Now heat is added to the system means this is going to be a positive term. Okay, this is going to be a positive term. Okay, this is also going to be a positive term. That means ds is going to be positive. ds is going to be positive. That means what? ds means s2 minus s1 is going to be a positive term. s2 minus s1 is going to be a positive term. That means what? Here s1 is less than s2. s1 is less than s2. That means what? When heat is added to the system, the entropy of the system increases from the previous one. Okay, whatever entropy it was having before, that thing is going to be less than whatever the entropy it has achieved after the heat is added. Okay, that means entropy of a system is increasing when we add heat to the system. Now let us consider that now heat is rejected from the system. Okay, now let us consider this one is case 2 and heat is rejected from the system. Okay, heat is rejected from the system. Now what will happen? Now dq is going to be negative. Okay, heat is rejected means dq is going to be negative, and t is always positive. Okay, t is always positive because it is the absolute temperature. Okay, now this is going to be negative. That means what? Here what will happen? ds is going to be negative. ds is going to be negative. That means what? s2 minus s1 is going to be negative. s2 minus s1 is going to be negative. That means what? We can see that s1 is greater than s2. s1 is greater than s2. That means what? When heat is rejected from the system, then the entropy of the system decreases. Okay, s2 is the final entropy after the rejection of the heat. That means what? When the heat is rejected from the system, then the entropy which has been achieved after the rejection is going to be less than that of the previous one. Okay, or the initial value of the entropy which the system was having. Okay, that means with the rejection of heat, the entropy of a system decreases. Okay, now in third case, let us take that it is an adiabatic process. Okay, reversible adiabatic process. If you consider case 3 as reversible adiabatic, what will happen? Adiabatic means there is no heat transfer. Okay, this is going to be the formula. Okay, this is going to be the formula. So reversible adiabatic means there is no heat transfer. There is no heat transfer means it is going to be zero. It is going to be nil. dq, change in heat transfer or the heat transfer or change in heat quantity is going to be zero. Now since the change in heat is going to be zero, that means what? The ds is going to be zero. ds is going to be 0 means s2 minus s1 is going to be 0. s2 minus s1 is going to be 0. That means from here we can write that s2 is equal to s1. Okay, s2 is going to be s1. Now for reversible process, we must know that for reversible adiabatic process, the process is always going to be isentropic. Okay, this process is always going to be isentropic. Okay, if you remember, we have said that in Carnot cycle, this was our cycle. Okay, now these two processes are adiabatic. Okay, now this was PV diagram. Okay, now if you draw the same diagram in TS plot, okay, or if you do the TS diagram of Carnot cycle, what will happen? This will be just a square. Okay, these two things are isothermal. Okay, the upper and lower bottom processes, the upper and lower processes are isothermal. So for here in this T, okay, in this T plot, these two are going to be isentropic. Okay, these two processes will maintain same temperature. Okay, since this is temperature axis, this is going to be same. Okay, and these two things are adiabatic or reversible adiabatic. Carnot cycle is completely reversible, which we have said earlier. Carnot cycle is completely reversible. Now these two processes are going to be reversibly adiabatic, and since it is reversible adiabatic, and we have just now derived that reversible adiabatic processes are isentropic, that's why this thing becomes parallel to T axis here. Since the entropy is going to be same in this path, and in this path entropies are going to be same, that's why these two things are parallel, and which is perpendicular to the S axis, okay, or parallel to the T axis. Okay, so just now we have learned that reversible adiabatic processes are always isentropic processes. Okay, so previously we have found out the entropy change for different reversible processes. Now we are going to find out the entropy change for different irreversible processes. Okay, now before starting the cases, okay, like in the reversible process we have directly written down case 1, case 2 and case 3. Now here, before writing down the cases, we need to understand something. Okay, now we all have derived this one. Okay, in the previous last to last board we have derived this one for reversible process. Okay, any dq by t term for reversible process is always greater than the corresponding term in irreversible process. Okay, and we have also said that this was the entropy change. Since this was same for all the reversible processes and only dependent on the endpoints, so this was the change in entropy. Now we can write down this. Okay, now that means what? This is always greater than this one. Okay, now to make this equal to this one, we need to add something to this one. Okay, if suppose this is greater than this term, okay, by some amount this term is greater than this term, and that amount if we add here, then this thing is going to be equal to this thing plus that amount. Okay, so for ds to be equal to this one, for ds to be equal to this one, we need to add something. We need to add a term here, then only this equation is going to be equal. Okay, or the inequality is going to be changed to an equation. Now this term is known as, okay, this term is known as entropy generation. Okay, this term is known as entropy generation. Now this thing is always going to be positive. If it is not positive, then there is no point of changing this into a equation. This thing must be always positive. Okay, and this thing changes from point to point. Okay, this thing changes from path to path. Okay, now what happens? This equation we have got from this inequation just to make sure that this thing is going to be equal to this one when we add a certain term to this. Okay, and this thing is always going to be positive. And for the reversible cycle, what happens? This thing is always 0. This thing is always 0 for reversible cycle. Why? In reversible cycle we have seen that up to this was the reversible process equation. Okay, this thing was completely 0 for reversible cycle. If they are in irreversible, this was reversible, then this was directly equal to this one, like this one. We have written this thing as directly equal to ds. That means in place of irreversible, if it was reversible, then it would have been directly equal to this one. The value of this one would have been 0 in case of reversible, and for irreversible it is positive. Okay, now let us take two irreversible processes from 1 to 2. Okay, let us take, this is C dash and this is D dash. These are the two irreversible processes from 2-1 and 2-1 and 2-1 via path C and 2-1 via path D. Now for the last 15 to 20 minutes we have been discussing that this is if we calculate the entropy of these processes, then entropy of these processes is going to be same, and that entropy is going to be equal to the dq by dt term for this reversible process. Suppose this is a dash. Okay, if we take a reversible process and we calculate the entropy change by calculating this one, then this is going to be the entropy change for any processes between the same endpoints, between 1 and 2, the endpoints, any processes is going to have the same entropy change, which is going to be this one, dq by t for reversible process. Okay, that means from here we can write that entropy change for path a 1 a dash 2 is going to be same for 2 c dash 1 is going to be same for entropy change of 2 d dash 1. Okay, that means only the entropy change is going to be equal to that of the reversible cycle entropy change, and all of these are going to be equal. But that does not mean that dq by t of 2c1 is going to be equal to dq by t of 2d dash 1. Why? Because we have said that in the last class, while we are writing the conclusions which we have derived, we have said that irreversible process, okay, dq by t for irreversible process is not a property. Sorry, this is not equal to. This is going to be not equal to. Why not equal to? We have said that this is not a property. Okay, we have said that this term is not a property. It is just a term or just a quantity which is less than that of entropy. Okay, this is just a term which is less than that of entropy. It is not a property. If it was property, then for same endpoints this value was going to be same. But since this is not a property and C and D are irreversible processes, that is the reason its entropy change is same, but irreversible process dq by t term is not same. Okay, irreversible process dq by t term is not same for path C dash and D dash. Only the entropy change is going to be same, because these terms are equal to entropy change in this path. Okay, this thing we need to remember. Now we can say that now we know that ds is going to be this plus this. ds is going to be this plus this. Now if you want to see that this thing is not equal, for path C and D this thing is not going to equal, not going to be equal. Okay, for path C dash and D dash this path is not going to be equal. This thing we have just written down here. Okay, this thing is not going to be equal for C dash and D dash, and if but this thing is constant, ds is constant, ds is same for all the processes. Okay, ds is same for all the processes, but this thing is changing. Now if this thing is changing and this thing is constant, that means this thing will also change. Okay, this term is constant, but this term is not constant for C and D. That means this term will also not be same for C and D. That means del S generation, okay, for 2 C dash 1 is not going to be equal to del S generation 2 D dash 1. Okay, since this is constant and these things are not same for C and D, that means this thing will also be not same for C and D. If this thing is constant or this thing is same and this thing is different, then this thing will never be constant. For this to be constant, the addition of these two must be constant. Okay, and if C and D are having different values of this term, then this term also must be different, so that their summation becomes equal to ds. Okay, so now case 1. Okay, case 1 is what? When heat is added to the system. Now this is the irreversible process equation for del S. Okay, or entropy change. For entropy change, this is the equation for irreversible process. Now when heat is added to the system, that means dq is going to be positive. dq is going to be positive, and del S is always positive, which we have said earlier. Del is going to be always positive. Okay, now if you see here, then what we are seeing that ds is going to be positive, because both the terms are going to be positive, so ds is going to be positive. Now if ds is positive, that means s2 minus s1 is going to be positive. That means what? s1 is less than s2. That means s1 is less than s2. That means in irreversible process also, when heat is added to the system, the entropy is going to increase. Okay, entropy increases there when heat is added to the system in case of irreversible process also. In terms of reversible process also, we have seen that when heat is added, entropy is going to increase. Okay, to see case 2, when heat is rejected from the system. Now similar equation we have written. Now when heat is rejected, this is going to be negative and this is going to be positive. Okay, one is negative and one is positive. Now there can be different cases. Okay, now first of all, let us suppose that this one is having a value of -5. Since it is negative, we are putting minus. Okay, and since this is positive, let us take the value is going to be 2. Okay, let us take the value is going to be 2. Now from here we can see that this is going to have a value of -3, which is negative. Now del S is going to be negative. That means what? S2 minus S1 is going to be negative. That means what? S2 is less than S1. Okay, that means S2 is going to less than S1. That means what? Entropy is decreasing. While heat is going to get rejected, the entropy is decreasing. Okay, now let us take another example. Okay, now let us take that this is ds. Okay, this is ds, and in place of this is negative. Okay, so in place of 5 we are taking this as -2, and this value is positive, then let us take this value as 5. Okay, we don't know what it is going to be, but we are considering the different cases what could happen. So first of all, we are saying that irreversible process is higher, but it is having negative value. This is going to be a smaller value, but it is having a positive value. Okay, so this can be one condition. Now in second condition, let us say that this is having a smaller magnitude but negative, and this is having a higher magnitude and positive. So this is going to give us 3, which is positive. Now if this is positive, that means ds is going to be positive. That means S2 minus S1 is going to be positive. If S2 minus S1 is going to be positive, that means what? S2 is greater than S1. S2 is greater than S1. Okay, that means what? Here entropy is going to increase. Here entropy is going to increase. That means we can say that if it is heat rejection from the system, irreversible process, energy or entropy may increase or may decrease. Okay, in third case, let us say that ds, this value is having, this is having a value of -5, and this is having a value of +5. Okay, this can happen. We do not know the equation, but we are considering the possibilities what could happen. Okay, so this is going to be 0. Now here, if ds is going to be 0, that means S2 is going to be S1. S2 is going to be S1, that is, this is going to be isentropic. Okay, now this is a case 2, when heat is rejected from the system. In this case, all the 3 can happen. All the 3 can happen, but for irreversible process, not for reversible process. Okay, this is for irreversible process. All the 3 things can happen. Entropy may decrease, entropy may increase, and entropy may remain same. Okay, entropy may remain same. Okay, we do not know for sure, but one thing we can say, if it is reversible adiabatic, we can say that it is definitely isentropic. But when it is isentropic, we cannot say that this is reversible adiabatic, because this thing we have got from an irreversible process which is not adiabatic, because it is rejected. It is rejected from the system. So neither it is reversible, neither it is adiabatic. still we are getting isentropic cases. That means we can say that if a reversible adiabatic process is there, it must be an isentropic process. But if there is an isentropic process, it need not be a reversible adiabatic process. Okay, that means all reversible adiabatic processes are isentropic, but all isentropic processes are not reversible adiabatic. This thing we are going to learn from here. Okay. Case is irreversible adiabatic process. Okay, irreversible adiabatic process. Now what? Since it is adiabatic, this is going to be 0. No heat exchange will be there, but this is always going to be positive. So from here we can say that this is always going to be positive. Okay, that means entropy del S is going to be positive. That means S2 minus S1 is going to be positive. That means S2 is greater than S1. That means what? Entropy is going to increase in case of irreversible adiabatic process. Whether in the case of reversible process adiabatic, it was isentropic. Okay, but here entropy is increasing. Okay, now if you consider, if you remember the adiabatic process. Now adiabatic process, if you take adiabatic process, there is reversible and irreversible adiabatic. Okay, now reversible adiabatic, if you remember, we know that del S was dq by t reversible. Okay, now for reversible process it was 0, adiabatic process it was 0. So in this case it was S1 equals to S2. Okay, entropy was same. Okay, since del S is equal to 0, del S is equal to 0, that means this was isentropic. S1 was equal to S2. But for irreversible adiabatic, what we have found out? We have found out that S2 is greater than S1. Now since S2 is greater than S1 for irreversible process, and S2 is greater than S1 and S2 are equal for reversible process, and S2 is greater than S1 for irreversible process, we can say one thing certainly, that if an adiabatic process is there, whether it is reversible as or irreversible, its entropy is never going to decrease. Okay, its entropy is never going to increase. Hardly it can be equal, or it can increase. Okay, worst case scenario, it can be equal. Okay, if it is completely reversible, then entropy is going to be equal. But most of the cases in irreversible processes, entropy is going to increase. That means we can say that if it is adiabatic, any adiabatic process, whether it is reversible or irreversible, its entropy is never going to decrease. Okay.